Hi students, in chapter 1 we looked at the material selection methodology where we are concerned with selecting the most suitable material for an application. And why is that so? It is so as to avoid failure of a component or part which can result in catastrophic breakdown on a larger scale. And so in chapter 2 we'll look at failure of metals. For this chapter on failure of metals, we will begin by looking at the consequences of failure followed by the 3 stages at which failure normally develops, after which we will dwell in detail the 4 main categories of metal failure, namely ductile fracture, brittle fracture, fatigue failure, and creep failure. In an engineering environment, equipment, or plant machinery, the failure of one unit or even a small component could lead to the damage of the equipment and thus may result in shutdown and therefore a loss of production. In a more serious note, failure would inevitably give rise to inconvenience and even the loss of lives. Therefore, understanding the different modes of failure would, in one way or other, help to determine the possible cause or causes of failure and even prevent recurrences. Let's now look at some consequences. The picture on the left shows a gas pipeline leakage in Taiwan, and this was the destruction that was left behind. Due to poor maintenance, a strip came off an Air Continental aircraft and hit Concorde, resulting in all 109 passengers on board killed. Do you know that metal failure was also responsible for one of the worst industrial accidents in history? In Bhopal, India, in December 1984, due to creep failure, a pesticide plant spewed poisonous gases into the atmosphere, and within 48 hours, 1,700 people died. Today, the death toll has reached or even exceeded 20,000. Now, let's look at the 3 stages of metal failure. Typically, failures whether due to cracking, corrosion, poor design or fabrication, environmental conditions or other causes occur gradually and usually develops in 3 stages. It starts with an initiation point which grows and subsequently result in propagation. The first stage could be detected during manufacture, though it may also develop during operation. The propagation stage is reached when the growth becomes unstable and comparatively rapid. With brittle materials, the process may occur with such rapidity, especially if unfavorable environmental conditions are suddenly imposed. When this condition takes place, catastrophic failure will result. Now, let us look at what can cause metal failure, so as to enable us to prevent it from taking place. As such, we'll look into these 7 key areas in our efforts to prevent and avoid failure. We shall start with poor design, followed by material selection, then look at material imperfection, deficiency in processing, and then end with operational causes like misalignment, improper service conditions, and inadequate maintenance. Poor design. In poor design, this commonly arises from the lack of understanding in the effects of stress raises, stress concentration locations, or stress distribution within structures. For example, the inadequate use of fillet radius at the change in section of a shaft or a similar part that is subjected to bending or torsional loading. Keyways and drilled holes are also sources of stress concentration, which will lead to early failure of metal parts. As such, under these circumstances, try as much as possible to incorporate radius at the corners in keyways and avoid situating holes near each other or the edges. In material selection, it is very important to take into consideration the operating conditions and requirements right at the beginning in the designing stage. Factors to consider includes the type of stress and loading, whether the stress system is static or cyclic, uniaxial or torsional. We also need to consider the environment. Here, we take the temperature into consideration, humidity, as well as the chemical and contaminants of the environment into consideration. Rate of wear or erosion is also particularly important when time factor is involved. And last but not least, the effect of temperature on its properties, such as ductile brittle transition temperature and creep. Imperfections in materials. Material imperfection refers to surface defects and internal flaws which can reduce the overall strength of a material. These flaws normally serve as origins for metal failure, and they can behave and act as stress bracers or stress concentration, initiating a crack or induce crack propagation leading to complete failure. Furthermore, material defects introduced during processing, such as gas porosity, may also be present in cast or welded products. Deficiency in processing. Deficiency in processing, such as cold forming and related operations such as deep drawing and bending, produces high localized residual stresses, cracks, microcracks, and loss of ductility. Surface defects and metallurgical changes caused by processing have an influence on fatigue strength, resistance to brittle fracture, and corrosion resistance. Moreover, machining and grinding can also leave residual stresses. Cracking in hardened steels are also known to result from severe grinding due to overheating and consequent softening. Misalignment. Misalignment of rotary shafts, gears, bearings, seals, and couplings is commonly a factor contributing to service failures. It produces additional undue stresses from friction, heat, and vibration, which can accelerate the failure rate, especially through fatigue. Improper service conditions. Very often, a machine, equipment, or device operates under abnormally severe conditions exceeding that as specified by the manufacturer. Exceeding conditions like speed, load, temperature, and type of environment could greatly reduce the life or even causes early failure of the component or machinery. Inadequate maintenance. Inadequate maintenance is frequently a contributing factor in service failures. Maintenance procedures should be thoroughly re-evaluated when failures reoccur despite regular scheduled maintenance. Testing and monitoring procedures should also be employed regularly at scheduled intervals to check for defects and the rate of deterioration, such as wear and tear. Now that we have gone through what causes failure and its consequences, let us now look at the 4 failure modes, starting with ductile fracture. Here, we shall ask, what is ductile fracture and how can it be identified? What are the causes and also how ductile fracture can be prevented? So, what is ductile fracture? Ductile fracture typically results from an overload of a tensile force to a metal that has the ability to deform permanently prior to fracture. As such, it largely occurs when the applied tensile stress exceeds the yield strength and is characterized by large amount of permanent deformation, necking, and a cup cone region with a fracture surface that is dull, rough, and fibrous. The diagram at the bottom right shows the stages of ductile fracture. Initially, the material will deform uniformly until a neck, which is the thinned down area usually at the weakest point along the loading direction, is formed. Next, within the neck, microvoids will begin to nucleate and form as the material deforms further. This is followed by void growth and it starts to link. At this stage, these voids will have coalesced to form a single bigger void, and sharing then occurs at the surface and fracture finally occurs. Then, how can we identify a ductile fracture? In summary, as mentioned in the previous slide,
A metal subjected to ductile failure shows considerable amount of permanent deformation with a cup cone region. The fracture surface would also be dull, rough, and fibrous. As ductile fracture occurs at stresses above its yield stress, this implies that one of the following could have occurred. The material was not strong enough. In other words, incorrect heat treatment could have been performed, or the wrong material was used. Next, the service condition or the loads differed from those anticipated by the designer or engineer. And lastly, abnormal loading conditions were applied. Before we end on ductile fracture, let's do a quick recap. Firstly, it is important that we know that ductile failure is due to the overloading of a structure or the application of a force exceeding that of the metal's yield strength. Secondly, we have to be able to identify or differentiate it from the other failure or fracture modes. Ductile failure can be identified by its characteristics of having 1. Large amount of plastic deformation. 2. A neck with a cup cone region. 3. Its fracture surface looking dull, rough, and fibrous. And lastly, SEM images will show dimples in fractography study. And last but not least, to know that the possible causes so as to prevent ductile failure, we use a stronger material for the first point. For the second point, the engineer will have to calculate, predict, and anticipate as much variation in service condition as possible. He can then redesign or use an alternative material where possible or incorporate a safety factor to mitigate this failure. The next failure mode that we're going to look at is brittle failure. Here, we'll learn more as to what brittle fracture is and how it can be identified through its characteristics. Similarly, as in ductile fracture, we will also look into the causes of brittle fracture as well as how it can be prevented. Let's start by asking what is brittle fracture. Brittle fracture is characterized by the very small amount of work absorbed. It typically occurs at low applied tensile stress, with great suddenness, displaying very little to no deformation. In other words, its crack propagation is abrupt and rapid. From the tensile graph below, we can confirm that brittle failure occurs in the elastic region, and so normally fracture takes place below the yield point. Bearing this in mind, let's proceed to identify a brittle fracture. As brittle fracture typically occurs within the elastic range, it fractures or snaps with little or no deformation. Its fracture surface is flat and it displays a shiny crystalline appearance, often with chevron or river-like markings. It is important to note that the chevron markings on the fracture surfaces of brittle failures usually point to the source or origin of the fracture, signifying that the failure originated from a severe stress concentration on the surface. The direction of crack propagation will therefore start from the source towards the opposite end. In fractography, scanning electron microscopy imaging shows cleavages for brittle failure, as its crack propagation is rapid, unlike that of a ductile fracture which shows dimples. Besides knowing how to identify a brittle fracture, it is important to know what causes brittle fracture too. For brittle failure to happen, three conditions are required. Firstly, the ambient temperature is below that of the transition temperature. I will go in detail in the next slide. Secondly, the presence of a notch. This can be a design feature, pre-existing crack, or a sharp defect. This attribute presents itself as a severe stress concentration point, magnifying the applied stress at the notch tip. In the presence of stress concentration, an applied stress might be amplified or concentrated at the tip of the notch, encouraging fracture to occur. The magnitude of the localized stress thus depends on the geometry and orientation of the crack or notch. And lastly, the existence of a tensile stress. To produce any fracture, a tensile stress is required in the material. This tensile stress may be an externally applied loading or an internal residual stress, usually a combination of both. As mentioned in the previous slide, let us now discuss further on the ductile brittle transition temperature, which is also known as DBTT in short. DBTT is defined as the range of temperature over which the fracture mode of a metal when notched rapidly changes from that of ductile to brittle. It should be noted that only BCC metals have a ductile brittle transition temperature. The transition temperature therefore depends on the size and thickness of the specimen, the rate and magnitude of the loading, and last but not least, the type of microstructure, which is, yes, BCC metals. Let's now look at how we can obtain the ductile brittle transition temperature, or the DBTT, of a BCC metal. The transition temperature is usually determined by using the Charpy V-notch test. In this test, the Charpy impact tester releases a heavy hammer that is attached to a pendulum from a known height to strike and fracture a notch sample over a range of temperatures. By plotting the result of the energy absorbed against temperature, the change of transition in fracture mode occurring over a range of temperatures can be found, and the DBTT is then determined using the mean energy approach on the energy to absorb fracture. In this slide, a typical DBTT graph is shown. With reference to the diagram, both graphs are identical in that as temperature drops, the amount of impact energy the metal can withstand also begins to gradually reduce, but still ductile to a point where a drastic transition to the brittle state takes place. Comparing the optimized steel to that of the normal steel, it can be seen that the standard steel starts to dip at a higher temperature as compared to the optimized steel, and therefore it will become brittle earlier and loses its ability to absorb shock should the temperature begins to drop. So, how do we prevent brittle fracture? Brittle fracture may be prevented by removing any of the three conditions necessary to cause it. If you still remember, the first is ambient temperature below that of the transition temperature. Second, the existence of a notch, and lastly, the presence of a tensile load. Alternatively, brittle fracture can be mitigated by the following: decreasing the carbon content to below 0.15%, or reducing the metal's exposure to high impact by decreasing the loading or impact rate. Subsequently, we can try to reduce the stress concentration and stress raises at the surface by decreasing the notch depth or increasing the notch radius. And last but not least, by modifying and refining the microstructure by increasing nickel content to 2 to 5% or reducing the grain size by adding grain refining elements such as aluminium and niobium. Now that we have come to the end on brittle failure, let's do a quick recap. Firstly, we must understand that brittle failure is associated with rapid crack propagation. Brittle fractures can usually be distinguished from ductile fractures by an almost complete absence of plastic deformation. Fracture occurs at stresses below the yield stress and are often flat and shiny. It is possible to trace the fracture path to its origin by interpreting the chevron markings on the fracture surfaces. With a brittle fracture, the fracture origin is often a notch or a small crack, usually on the surface. When examined microscopically, brittle fracture may be transgranular or intergranular, and scanning electron microscopy images reveal cleavages. So, what causes brittle failure? As discussed previously, the three factors are ambient temperature lesser than transition temperature, presence of a notch, and thirdly, the existence of a tensile stress. Therefore, to prevent brittle failure, we can remove the above causes. For the first point, we can do that by ensuring that the DBTT of the metal is above the operating temperature of the metal. And for the second, we can improve the surface condition or redesign where possible to reduce or remove stress concentration points. For example, by not placing holes near one another or near the edges, by removing or reducing sharp corners, by adding radiuses and chamfers, etc. For the third point, we will seek to reduce, redirect, or remove the applied tensile stress. Now, before I end and move on to fatigue failure, it is important to note that fracture of brittle nature, including fatigue fracture, which I will cover next, should be avoided, as its occurrence is not only sudden and rapid, but also catastrophic and without warning. In this slide, I've summarized and tabled a chart comparing side by side the differences in occurrence, identification, and causes between ductile and brittle failure. So, do pause the lecture video and take a few minutes to review the table. Similar to previous sections, let's now look at the learning outcome for this section on fatigue. I will start with what is fatigue failure. Then we'll look at how is it quantified and how to identify it. Knowing this, we'll then look into the causes and to how to prevent fatigue failure. The term fatigue is used to describe the failure of a material under a repeatedly applied stress. For this failure, the stress required to cause failure, if applied in a large number of times, is much less than that necessary to break the material or metal with a single pull. These stresses are usually dynamic and changes with time. Example, in live loads, temperature, pressure, wind loads, or even seasonal. Additionally, the change in stress loading can be cyclical or random. A key point to note about fatigue is that a component can fail even though the maximum stresses that are applied to it is less than its yield stress, and that it accounts for approximately 90% of all mechanical failures. As such, how can we measure or quantify fatigue? The fatigue properties and data of a material can be obtained by subjecting it to repeated loading using a Wöhler machine as shown in the slide here. From components that are small to items that are big, the fatigue properties of different metals can be obtained using the Wöhler machine. In this diagram, an airplane propeller blade is being appraised. A series of specimens are subjected to reversals of stresses, each at a different value, until failure occurs, or until 10 million cycles have been endured. The total number of cycles to failure is then recorded, and a stress cycle curve is plotted from which we can establish the relationship between the stress and the number of cycles to failure for any given particular type of loading. In this slide, a typical stress cycle curve is shown. When stresses are high, the number of cycles a metal can endure is lesser than that as compared to a lower stress. Do note that the x-axis is locked as the cycles to failure can run into millions. Now, let's take a closer look at fatigue limit, which is also commonly known as the endurance limit. It is interesting to note that there are two types of fatigue behavior that is commonly encountered. The first, like the one at the top with a horizontal section, it is commonly associated with ferrous metals like different types of steels, whereas the second curve is commonly associated with non-ferrous metals and alloys like magnesium, copper, and aluminium, etc. The fatigue or endurance limit is thus defined as the limiting stress below which a metal will withstand an indefinitely large number of cycles of stress without failure by fatigue. In the latter case, as mentioned earlier for the lower curve, when non-ferrous metals do not show true endurance limits, the term endurance strength is used. It is defined as the stress at which fatigue failure would not occur before a specified number of cycles. Now that we have learned how to quantify fatigue failure, let us now look at how we can identify it. Fatigue fractures exhibit little or no visible signs of deformation, and for this very reason, it is very difficult to spot, particularly at the beginning stages. A fatigue fracture usually starts at a point of high stress concentration, normally a crack or a very narrow opening at the surface, which then advances and grows as the stressing is repeated until it extends through a considerable part into the material. When the crack reaches a critical mass, final fracture then occurs suddenly and disastrously. Although fatigue fracture is brittle in nature and does reveal areas of brittle fracture under fractography examination, the fracture surface has a unique appearance that is different from that of brittle failure. It consists of two areas where one portion is smooth and shows pitch mark striations spreading out from some discrete points indicating where the fracture was initiated. These striations are often a feature of service failures associated with non-uniform conditions and intervals of rest. The remaining of the surface, which indicates the final tearing, will display either a crystalline or fibrous appearance and therefore can be a brittle or ductile fracture or even a combination of both, and this occurs when the area can no longer sustain the load. To combat fatigue, we can target its source. Since we have learned earlier that fatigue usually starts at a point of high stress concentration, which may be a design feature, a crack, or a very narrow opening at the surface, we can reduce the stress concentration by improving on three key factors through: number one, improving the design at the beginning during the designing stages; number two, improving or selecting the most appropriate processing method; and lastly, improving the surface conditions such as introducing compressive stresses. Remember this earlier slide? Let's recap and take a look at the specimen with holes drilled near each other or other forms of stress raises like notches, keyways, screw thread, machining marks, and other irregularities, etc. These artifacts produces stress concentration at these points and raises the level of stress, and therefore it should be minimized, as these can act as starting points for the promotion of fatigue failures in the material, thereby lowering the fatigue life of the component. Bearing in mind what we have just discussed, it is important to minimize and or avoid creating such areas of stress concentration during the design stage where possible. For example, we can have rounded contours, add generous radius, fillet, chamfers to sharp corners, and also redesign the components to have a more uniform section, for example, a tapered shaft instead of a stepped shaft. Additionally, stress concentrations can also be introduced during processing and should be avoided. Avoid welding and adopt a forge and machine part instead, as high intensity heat and temperature gradient of the welding seam to the surrounding material can generate internal stresses due to microstructure changes and non-uniform cooling. Defects such as cracks, voids, and inclusions are characteristic of certain processes like casting and powder processing methods, and as such, care and efforts must be taken to reduce it. Additionally, as fatigue usually starts at the surface from a surface defect such as a crack, a scratch, or surface roughness, the surface finish should thus be smooth and flat, and this could be achieved by grinding, lapping, or polishing. With the surface being the most vulnerable area susceptible to defects as previously discussed, we can, besides improving the surface texture, also harden the surface to improve fatigue resistance. We can achieve this in three ways, namely shot peening, co-rolling, and case hardening, where the fatigue strength of a metal is improved by introducing residual compressive stresses to the surface layer to counter the effects of tensile stresses during operation of the part. These compressive stresses can be introduced via distorting the crystal grains at the surface by shot peening, where a stream of steel shots is made to impinge on the surface, or by co-rolling, where the metal is inserted between rollers and then compressed and squeezed. In case hardening, a hard surface layer containing nitride or carbide phases is produced by allowing nitrogen or carbon to diffuse into the surface of the steel at elevated temperatures. This nitriding and carburizing process will be covered in greater detail in Chapter 6. Now, before going into our last failure, creep, let's summarize and recap on what we have learned on fatigue. It's the failure of a metal under a cyclical dynamic stress. It shows little or no deformation, and its fracture surface normally shows two areas, where one portion is smooth displaying beach mark striations spreading out, and the other portion the final tearing zone. The cause is due to stress concentration originating from stress raisers like notches, keyways, screw thread, machining, and other irregularities stemming from poor surface conditions. And to prevent fatigue as far as possible, avoid stress raisers in the design stage and avoid introducing stress raisers during processing. Alternatively, we can instead try to improve the surface condition by introducing compressive stresses through these methods like shot peening. Creep is an important topic in metallurgy, and to an engineer in charge of selecting metals and materials, this subject is one that he must be aware of. Creep-related failures can happen frequently and are hazardous to both property and human life. So in this section, like previous, we will ask what is creep failure, and instead of why, we ask when creep is important, and we will then proceed to quantify it and see how to prevent creep. So, what is creep? Creep is a type of metal deformation that occurs at stresses below the yield strength of a metal, most noticeable at elevated temperatures, and metals that undergo excessive creep deformation can oftentimes fail completely. From year 1, we have learned that the yield strength defines the stress at which a metal begins to deform plastically. As such, creep is unique in the fact that it is a phenomena whereby a material can plastically strain even though yield stresses have not been reached. So, creep is defined as a time-dependent plastic deformation under constant stress at elevated temperature. With regards to the temperature, it becomes especially important for metals when the operating temperature is greater than 1/3 the melting point in Kelvin. So the question now is, when does creep become important? It becomes important when metals and alloys are stressed at a temperature in excess of about 1/3 the melting point in Kelvin. For example, lead and tin, whose melting temperature is approximately 231 degrees and 327 degrees respectively, can creep at room temperature, while molybdenum, tungsten, and nickel-based alloys creep at about 1000 degrees Celsius. Let's look at an example. The creep for lead after calculation can take place from a temperature as low as negative 73.8 degrees Celsius. As such, it is important when considering what metals to use for steam and chemical plants that operates at 450 to 550 degrees, or gas turbines which are working at higher temperatures of between 800 and 900 degrees, or even higher, in excess of 1000 degrees for furnace parts. Let us now look at the three stages of creep. The typical behavior of a metal under a constant load at a specified temperature can be illustrated by plotting the strain versus time curve. After a certain amount of instantaneous deformation as indicated on the diagram, the curve shows three distinct stages, namely primary creep, secondary creep, and tertiary creep. Primary creep is the first stage of the deformation process. At this stage, elastic deformation is initialized. During the primary creep stage, this deformation occurs more rapidly at first and then slows down with time. The reduction in the creep rate could be interpreted metallurgically as a result of strain or work hardening. In other words, dislocation movement is becoming more difficult. Secondary creep then takes over. In this stage, the strain rate begins to stabilize and becomes constant and occurs relatively slow when compared to the first stage and the final stage of the creep. This is because no microstructural damage has taken place yet, as work hardening is balanced out by thermal softening. During this stage, the grain size will also affect the strain rate, as metal with finer grains will creep faster than metals with coarser grains. Into the final stage of creep, also referred to as tertiary creep. It will commence when damage to the microstructure of the metal takes place. Here, the strain rate accelerates as the microstructure deteriorates with the formation of cracks, necking, and structural changes. After enough microstructural voids have been created, the metal eventually fractures and fails completely. Then, how is creep quantified? Creep can be quantified using a creep curve which plots the strain versus the time. Creep, besides the constant load, is temperature dependent. The higher the temperature a metal is exposed to, the higher the creep strain. Likewise, the stress induced on the part. Bearing all this in mind, let's see how we can prevent creep. The effects of creep can be circumvented or reduced through several different methods. One way to reduce creep is to lower the working temperature that the metal being used is exposed to. As this is not always possible, a higher melting point metal or alloy should be considered instead. Another method is to reduce the constant load that the metal has to withstand. But again, this may not be achievable depending on the situation or application. Using a large grain or single crystal alloy can also help reduce creep due to less grain boundary slip that occurs. And last but not least, certain metals can be strengthened with specific alloying elements. These can avoid creep by eliminating microstructural vacancies through solid solution strengthening and precipitation hardening. Before we end this topic on creep, let's recap. Creep can be defined as a time-dependent plastic deformation that takes place under a constant stress at elevated temperature. Its deformation shows three distinct stages, where primary creep shows rapid extension at a decreasing rate due to strain hardening, followed by secondary creep, which proceeds at a constant rate as thermal softening balances strain hardening. This eventually leads to the tertiary stage, with increasing strain rate leading to complete fracture. Prevention methods include the use of alloys with high melting point, alloys with coarse grains or single crystals. Last but not least, alloys strengthened through solid solution, precipitation, or dispersion hardening process. We have now come to the end of this chapter on metal failure. I hope you have gained an insight into how metals fail and its serious consequences should it fail.